the intensity of the signal is dipole moments. So the greater the dipole moment, the stronger the signals. And there is another factors that can contribute to the intensity of signals in an infrared spectrum. Let's consider groups of signals at just below 3000 centimeters to the minus one. So this is a 3000. And if you draw a line, you see that you have a strong signals just below strong or high intensities. So this is due to the absorption of CSP3H. So the intensity of these signals is due to the number of CH bond giving rise to the signals. And we know that almost all organic compounds will have a large number of CSP3H. And so this contributes to the strong signals at just below 3000. This is due to the CSP large number of CSP3H. So the second factor is the number of the bonds. We have some small exercises. So the first one, comparing the intensity of the CC double bond in different compounds. So in the first pair you have an alkene, and in the second you have a alkaline chloride. Alkyl chloride. So you have a chloride at the double bond, and now you have to compare predict the intensity of these two CC double bonds. So in the first case, you see that these two carbon atoms at the double bond, they are connected to the alkene group. And so they are not so different in terms of electronic properties or electron densities. But in the second structures, you see that the carbon on the right is directly bonded to a chlorine. And you know that chlorine would have an induction effect on that carbon. And therefore, the carbons with the chlorine atoms and the carbons with the two alkyl groups will have different electronic properties. And therefore, this CC double bond will have a higher or greater dipole moment. Yeah, the one with the double bond, with the chlorine at the double bond, will have a greater dipole moments. And therefore, we suppose that it will have a stronger CC absorptions signals. Okay, in the second compound, in the second pairs, you also have CC double bond. In the first case, each atom at the double bond is directly bonded to a chlorine atom. So these two carbon atoms are quite similar. But in the second structure, you see that one of the carbon at the double bond is bonded to two chlorine atoms, and two chlorine atoms have induction effect. And so these carbons, the one that I highlight, will be very different from the other one in terms of electronics properties. And so this one will have greater dipole moment. And we guess that it will have stronger CC, the absorption wave number for CC, stronger signals for the CC double bond. Okay. They found that the CC double bond in in cyclohexane node produce an unusually strong signals explained using resonance structures. So in order to draw resonance structure of this one, we start actually. I should start first at the CCO double bond, and then I draw the second arrows from the CC double bond toward the CO double bond, and therefore I obtain another resonance structures in which one of the carbon atom at the beginning double bond is positively charged. And you see that the second one, this one, nearly have no, this one has no charge, nearly has no charge. But this one is positively charged. So we can think that this will have a strong dipole moment. So strong dipole moment will produce strong signals because of the different in terms of electronics property of the two carbon atoms in this double bond. And we explain it by drawing resonance structures. Okay. Are you still following me?
Yes.
Okay. Okay. Thank you. Okay, the next questions. Trans Butyins does not exhibit signals in the double bond regions of the spectrums. So trans Butyins is an alkene with a very symmetrical structures. Trans-but-2-ene. So we guess that the dipole moment of the CC double bond is nearly zeroed. And a symmetrical bond with small or zero dipole moment will inefficiently absorb infrared light or infrared radiation. And therefore it has a very weak or even no signal at all. Yeah? Very weak or no signal at all. However, the infrared spectroscopy is still possible to identify the presence of the double bond. So which signal we use in this case to identify the CC double bond? If we cannot, based on the signal of the we don't have a signal for CC double bond. So which kind of other signal that we can use to
sorry, sir, your microphone is turned.
Sorry, can you repeat?
Không phải anh đâu, không phải đâu anh Đạt ơi, hình như là do loa của anh đấy. Em vẫn nghe được thầy nói mà.
All right. Biết ngày nào mà hết Covid để chúng ta đi học nhỉ, đúng không? Okay, who have the answer for this? We cannot base on, yeah. So we have the very exact answers from three. We still have some CSP2H bond. And CSP2H bond will have about 3 absorption wave number of 3,100 centimeters to the -1. So just on the left of 3,000. Okay, very simple. Okay, the last characteristic of the infrared signal is the shape. The shape. So there are actually only two kind of shapes in for infrared signals. So this picture shows you how a broad signals looks like. So it's broad. It's very clear that it's very broad. Yeah. broad means it has a large base. The trigonal has a large base. And the point is quite broad. The point of the peak signal is quite broad. A sharp signals have a short or small base, more base, and a sharp point. The point is sharp. So these are the two typical shape of a infrared signals. So let's talk about the effects of some effect of hydrogen bonding to the shape of the signals. You know that you learn from organic chemistry one that alcohol exhibits hydrogen bondings. The hydrogen bonding formed between the hydrogen atoms of one OH group with the oxygen of the others OH group. So this the hydrogen of one OH. It has a positive charge because of the induction of oxygen, and because of this positive charge, it can have a static attractions with the lone pairs, one of the two lone pairs on the other oxygen atoms. So it is an static attractions between two center of different charges. And one effect of hydrogen bonding is to weaken the OH bond. Why does a hydrogen bonding can weaken the OH bond? Because when a hydrogen bond is formed, you see that the hydrogen atom is pulled far away from the oxygen that is now bonding with. Yeah. The hydrogen is now pulled to the oxygen on the other molecules. It is pulled away from this oxygen. So this bond, due to the hydrogen bonding, the OH bond become this bond become a little bit longer. And longer means weaker. So one effect of the hydrogen bond is to weaken the OH bond. So in solution where you have high concentration of alcohol, we say concentrated alcohol, you always see broad signals because of the existence of hydrogen bond. At any given moment in time, the OH bond in each molecule is weakened to a different extent. Okay, sorry. So because of the formation of hydrogen bonding, the OH bond do not have a consistent bond strength, but it changes. So some molecules are barely participating in hydrogen bonding, while the other molecules are participating in hydrogen bonding to varying degrees. And the infrared spectrometers will record all of this kind of OH bond, and the result is a broad signals. Liquid hydro thì làm yếu đi cái liquid OH đúng không? Nhưng mà nó làm yếu theo rất nhiều mức độ khác nhau, và cái máy phổ hồng ngoại thì nó không phân biệt những cái mức độ đó, mà nó ghi một cái tín hiệu tổng cộng của tất cả cái dạng đó. Và do đó mình thấy có một cái phần rộng về vậy. Rộng này tương ứng với nhiều loại liên kết OH tham gia các kiểu liên kết hydro khác nhau. Okay. The shape of an OH signal can be different when the alcohol is diluted in a solvent, that in an inert solvent that cannot form hydrogen bond with the alcohol. So in such an environment, it is likely that the OH bond will not participate in hydrogen bonding interactions. The solution is so dilute that every alcohol molecules are far apart, so far apart that they cannot make hydrogen bondings. And in this case, you see narrow signals for the OH absorption. When the solution is when the concentration of the alcohol is medium, then you can observe both kind of signals, sharp and broad, narrow and broad. So this is examples of that kind of solutions. So above from, if you remember, from 3,200, yeah, 3,200 to 3,600 is the regions for the absorption of the OH in general. In this case, you see two different kind of signals. One is narrow and one is broad, and the narrow signals correspond to OH without hydrogen bonding, and the broad one from 3,500 to 3,200 corresponding OH participating in hydrogen bonding with different extent. Okay. Vậy có thể là có hai loại nhóm OH đúng không? Nhóm OH mà không tham gia liquid hydro thì nó sẽ cho tín hiệu sắc nhọn, còn với nhóm OH tham gia liquid hydro thì nó tù. Và tù là vì nó là trung bình của, nó là tổng hợp của rất nhiều các cái dạng OH bị biến đổi mức độ khác nhau do liquid hydro. Okay. Okay, so depending on the condition, an alcohol will give a broad signals or a narrow signals or both. Okay, as explained previously, the concentrations of an alcohol can be selected such that both a broad signals and a narrow signals appears simultaneously. In such cases, the broad signal is always to the right of the narrow signals, never to the left. Explained. Trong cái dung dịch nồng độ vừa phải đúng không? Thì chúng ta thấy là nó luôn luôn xuất hiện hai loại tín hiệu đúng không? Một cái shaft và một cái rod. Nhưng mà nếu căn cứ vào trục chúng ta thấy là cái rod bao giờ nó ở phía tần số hấp thụ nhỏ hơn so với cái shaft. Ta giải thích nào.
Because the abort signal is caused by the weakened bond from the
Yep.
free bond.
Thank you. That is the answers. So this the weakened OH. Yeah, that said is the weakened OH due to hydrogen bonding. Why is that weakened? Because when the hydrogen bond form, you see that the hydrogen of the OH is pulled away from the oxygen due to the static attractions of the lone pairs on the oxygen of other molecules. It pulls this hydrogen is pulled away from the oxygen that it is bonded to. So it means that this OH bond become longer, or in other words, it becomes a stretch. And become longer or become straight means weaker. Weaker will correspond to smaller absorption wave number. Okay, thank you. So the broad peak is always on the right of the narrow signals. Okay, carboxylic acid exhibits similar behaviors, meaning that they also make hydrogen bonding, but in case of carboxylic acid, the hydrogen bond is much more stronger. So let's have a look at these spectrums of an acid. So you see that you have a very broad signals ranging from about 3,600 to about 2,200. You don't have to remember exactly the numbers, just about. And this very broad peak correspond to the absorption of the OH in the carboxyl group. And you see that in this case, it's overlapped also the signals of the CH, overlap. The absorption of CH, in this case, CSP, SP2 and SP3 are overwhelmed. I don't know the word overwhelmed. This is overwhelmed by the absorption of the OH group. So you don't see, you may not see the absorption of the CH bond in these regions. And also you see typical strong signals for the CO double bond in the carboxylic group. So it's quite easy to identify a carboxylic acid due to these two typical signals, especially the ones ranging from 3,600 to 2,200 centimeters to the -1. Strong hydrogen bonding. So the very broad signals characteristic of carboxylic is resulting in hydrogen bondings. In alcohol, you also have hydrogen bondings, but normally hydrogen bonding of alcohol is formed in an open chain framework. But in carboxylic acid, the hydrogen bonds make rings, and this is much more stronger than the open framework. So this is open framework. Or open network. While those formed in carboxylic acid is a ring. Yeah. And so it's much more stronger. And this hydrogen bond of carboxylic is also explained for responsible for the higher boiling point, very high. Yeah, because when you heat an alcohol, from its liquid state, then single molecule will leave the liquid state. So this is single molecule. But when you heat an acid, yeah, I make it appear like this because of it's a dimer. Let's say it's a dimers, and when you heat it and make the acid leave the liquid phase, then in gas phase it is still dimers. And dimer means heavier. So you always need higher temperatures to evaporate a heavier molecule. Understand?
Yes.
Okay. Làm bay hơi có phải là evaporate không? Làm bay hơi là evaporate đúng không?
Evaporate.
What?
Evaporate.
Okay,
Yeah.
okay. I have a lot of problem with pronunciation. Okay. Evaporate. Okay. Thank you. So this is also explained for the very broad signals of the OH in carboxylic acid, different from the OH on the alcohol molecule. Evaporate. Okay. So the infrared spectrum of a carboxylic acid is very easy to recognize because of the characteristic broad signals cover 1/3 of the spectrums, as well as the strong and broad signal of the carbonyl group at about 1,700 centimeters to the -1. About, I think it's about. Okay. So we have some small exercises to practice. So I'm going to show you a number of spectrums, and you have to identify whether each spectrum is correspond to an alcohol, to a carboxylic acid, or to or neither. Mình sẽ có một loạt các cái phổ hồng ngoại và bây giờ mình sẽ thử nói xem là các cái phổ này thì ứng với ancol hay là ứng với axit hay là không phải hai loại đó. Okay. So for an alcohol you have to, yes, thank you, that's right, maybe an alcohol, right, that is a very good exact answer. So an alcohol you need to look for a broad OH from about, I think, 3,600 to 3,200. Broad, but not very broad. And for carboxylic acid, you need to look for a very broad. Yeah. So very broad means from 3,600 to even 2,200. And also you have one more characteristics of the infrared spectrum for acid is strong carbonyl absorption at about 1,700. So this one, this one has, this is, I think, for CH, yeah, and this is for the OH of an alcohol, not for an acid. Right, so this is for alcohol. Right. So no signal here. No broad signal above 3,000. So I think it's neither corresponding to a alcohol nor an carboxylic acid. So neither. I think maybe, yes, maybe an alkene. But in this case, you just have to decide if it is an acid or an alcohol only. You don't have to care. Yeah, maybe. Yeah, this is maybe for the C double bond. Right. Sorry. I agree. Yeah. No, not an alkane. I think it might be an alkene. And 3,000 is here. 3,000 is here, right? So if you draw a line, if you draw a line from 3,000, you see that you have some signal on the left. On the left means maybe SCSP2H. So I think it might be an alkene. Okay, thank you. Okay, This one, yeah, clearly it has two characteristics, right? Right, thank you. It is an acid. So an acid has a very, very broad signals ranging from about 3,600 about to 200 to 2,200 centimeters to the -1. And this range includes the absorption of OH and also the absorption of different kind of CH. So S might be sp3, CSP2, and also CSPH. You cannot see anything clearly in this range. And this is a typical signal for CO strong. So yes, this is an acid. Thank you. Okay. Yeah, but this one may be an alkane, I think, because you don't see any specific signals. Let me draw 3,000. Yeah, this one may be an alkane, so no broad signals. Above 3,000 and about this range, no signals, no strong signals. So it cannot be an acid. It is neither an acid nor an alcohol. So this one might be an alkane. Okay, I think again you have here and might be an so you don't have right an alcohol, right. Thank you. So no CO, right? 3,000. Yeah. So saturated only. So this is 3,600. This point, and about 3,100. So this is OH of alcohol. Yeah, this is maybe a saturated alcohol. No CC also, I think. No CC and no CO absorptions. So maybe it's saturated alcohol. Thank you. Okay, again, this one looked very typical, yeah, acid. Okay, you know the answer already. So this is typical broad. The dimers, and this is strong signals for the absorption of CO. So maybe this one is also a saturated acid, carboxylic acid. Okay. Okay, I think maybe that is enough for today. So if you have any questions, then just ask. If not, then we say goodbye, and I think the last section will be discussed in the next lectures. Yeah, do you have any more question or request?
Em muốn hỏi nhỏ một xíu ạ, là nếu mà dựa một cái hình này thôi ạ thì thầy có gọi được tên cụ thể cái chất đấy không?
Impossible. Yeah, my answer is impossible. You don't know how many carbons, yeah, and you don't know the chain, straight chain or branch. You don't know. So you need others. You need others methods like mass and nuclear magnetic resonance spectrometries in order to have the full set of information for this compound. Thực ra thì câu Tuấn Anh hỏi là có hai cái trả lời. Thứ nhất là nếu như mình mà học kỹ hơn một chút nữa về cái phần fingerprint region ấy, thì thực ra mình có thể nói được nó là mạch hở hay là mạch vòng, mạch thẳng hoặc mạch nhánh. Mình có thể nói thêm cái thông tin đấy nếu như mình quan tâm đến cái vùng dưới 1500. Cái vùng dưới 1500 thì mình có thể nói thêm một chút thông tin nữa, cái vùng từ dưới 1500 này, cái vùng gọi là vùng fingerprint ấy, thì mình có thể nói thêm nó là open hay là ring này, open chain hay là ring này, nó có thể là branch hay là straight, có thể nói thêm thế thôi. Nhưng mà nói cái này là bao nhiêu carbon thì impossible, với phổ ngoại là impossible. Mình phải kết hợp với MS, kết hợp với NMR nữa, thì mình sẽ nói ở các buổi tiếp theo. Ok, nói chung là phải phối hợp với phương pháp phổ thì nó sẽ ra một cái bức tranh tổng thể hơn về cấu trúc. Trong đó như chúng ta biết ở hữu cơ 1 ấy, thì cái NMR là cái phương pháp toàn diện nhất. Okay, so any more questions? No? Okay, so let's have a nice evening, and I think you have learned from 1 p.m. right?
Yes.
Yeah, okay, I think yes. So hungry now, I think also. Okay, so have a nice evening. Bye.
Bye
Bye.
thầy ạ.
Yeah.
Bye thầy.
Bye. Okay, thank you.
Em chào thầy ạ.